Okay, so this is going to be the same lesson that we did in class, but I think some of you were having some trouble digesting it all at once because it was an awful lot. So let's take a look at how we link up these different types of combination problems. So one of the types of problems is how many different words can you form if I give you a bunch of one letter and a bunch of another letter. And for what we're doing now, we're only limiting this to 2 letters at a time, 2 different types of letters. So I've already listed off all the ways. There are 10 of them. Now that doesn't really tell us much. The formula for it, though, is if all these letters were different, they were each unique, then I'd have this many ways of coming up with words because I'd have 5 choices for the first letter, 4 for the second, 3 for the third, and so on, 2 and 1. So 5, 4, 3, 2, 1. The only problem with this is that I've got some of the same letters in there. So this would be like if I had words like this, A, B, C, D, E, and B, A, C, D, E, stuff like that. But the problem is I've got 2 letters that are the same, two B's, and then I've got 3 A's too. So the way to get rid of those multiple versions of the same word is I have to divide out the number of ways to just arrange those 3 A's that are contained in these bunch of words. And so that's going to be 3 factorial. And I have to divide out the number of ways to arrange the 2 B's within all the words, and that's 2 factorial. And if you calculate that, you get 10. So this is one that hopefully you learned last year. I think it takes a little while before it really sinks in how that works. So part of it is just kind of trusting it for now and linking this idea to all the other ones. So this right here, again, we can also write it as 5 choose 3, which I think in this context doesn't make a ton of sense. And you can also link it to this 5 choose 3. Now the reasons that we link it to me in my mind is mainly because the equation for these 2 guys is identical to this. Normally I would just think of doing the actual factorial equations and not worry about these 2 guys, but they are all equal. Okay, so that's that one. That's the words example. Now down here we've got a Pascal triangle example. So the goal is to figure out how many ways there are to get from A to B, and you can only move down one step at a time. So like if you're at A, you can go left or you can go right, and that's it. That's the first step. So at this point we've taken no choices, and then at this point we've taken one choice. I've gone either left or right. Then I'm going to make a second choice. I'm going to go left or right here if I went left originally, or I'm going to go over to one of these 2 points here. So at this point I've made 2 choices, and then the next one will be 3 choices, 4 choices, 5 choices. I included a 6th line here, or really it's a 7th line, but B is actually on the n equals 5 row. So if we actually fill in a whole bunch of these, I'm going to do this relatively quickly. So let me just get this out of the way. So I've got all these right turns that are possible, all these left turns that are possible. Left, 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 left. Right, 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 right. Left, left, left. Right, right, right. Left, left. Right, right, and left. Okay, so one of the things to note, whoa, did stuff get moved over somehow? Left here, left here. Somehow those moved, I don't know why. Left here. Okay, one of the things to note here is that in this like slanted row right here, I've taken no right turns to get to any of those points. So I can say this slant row is the right turn equals 0 row. And the only way to get to any point in this row is to be in this row and take 1 right turn total. So every point in this second green row had 1 right turn involved. No matter how I got to those points, I only took 1 right turn. In this one, I'd take 2 right turns. This one, I'd take 3 right turns, 4 right turns, and so on. So, really, when you start to map out all the different paths to get from A to B, like this one right here, that's 2 L's and 3 rights. 2 L's and 3 R's. This would be an R. So I've gone left, left, right, right, right. Then if I mapped out another one, like this one, left, right, left, right, right. Left, right, left, right, right. It doesn't take too long before you start to realize that this list that I'm making right here is going to be all the different ways I can put together 2 L's and 3 R's. So really, it turns into a problem just like this one right here. So how many words can I form with 2 L's and 3 R's? Well, that's going to be exactly the same type of problem. So it's going to be 5 factorial over 3 factorial, 2 factorial, which is 10. Notation-wise, we can call that 5 choose 3, or write it like this, 5 choose 3. I think the 5 choose 3 makes a little bit more sense in this case. The idea here is that if I don't choose left, then by default, I'm going right. And so really, if I say you're going to make 5 choices and 3 of them have to be right, then it's the same thing as saying you're going to make 5 choices and 2 of them have to be left. So it doesn't really matter if I say 5, I'm going to choose 3, or 5, I'm going to choose 2. This would be 3 rights versus choosing 2 lefts. Right? It doesn't matter. They're really the same path, ultimately, if you think of them that way. So these two things both end up being 10. So the number of ways to get here is 10. Okay. Another useful thing with this triangle is that once you have all the R's listed here and the N's listed over on the left, you can figure out what, say, this point should be in terms of the N choose R notation. Because N is 5 and R is 1. So this spot right here is actually 5 choose 1. And there's a nice pattern to it if you just go all the way down. This one's 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, and so on. All the way up to 5 choose 5. Another way you can get this 10 right here is by just kind of saying to yourself, okay, well, I'm starting at the top. What color can I use? I've got a black. So I'm starting here. There's only one way to start. And there's only one way to get to any of these points on the side. You'd only take left turns. And there's only one way of getting to any points over here. You'd have to take right turns. To get to this point, the only way to get to there is from this one or this one. Because those are the only ways, those are the only ones that have arrows that lead to it. So since there was one way of getting to this point and one way of getting to this point, there's a total of 2 ways to get to here. Now if I look at this point right here, there were 2 ways to get to that one and 1 way to get to this one, and these 2 were the only 2 to get to this point. So this one would have to have 3 total paths. And if I keep filling this in using probably the method you already knew for Pascal's triangle, but maybe didn't know quite why, if I keep filling this in, then you can see right here 6 and 4 are going to add up to the 10 that goes right there. Okay, so let's keep going. Alright, you flip a coin 5 times, how many ways can you get exactly 3 heads? Well, okay, so I'm flipping a coin. I basically have 2 outcomes every time. It's heads or tails. And if I flip it 5 times, I'm going to need 3 heads and 2 tails. Now it might be that the 3 heads are first and then the 2 tails. It might be that I get 2 heads, then a tail, then a head, then a tail. But these are all the different ways. If I list out all these things, I want to come up with every combination of 3 heads with 2 tails that I can get. Well, there's a lot of them. And in fact, this is exactly the same problem that we did here and here. So really, I know that there's going to be 5 choose 3 ways of doing it. Now the way to think about this is I'm flipping it 5 times, so I have 5, you could think of them as choices to make, and I need to choose heads 3 times. So it's 5 choose 3. Now that works because the other 2 outcomes, I don't get a choice. If I picked heads 3 times, the other 2 have to be tails. So that's really no different from me saying flip a coin 5 times and get exactly 2 tails, because then the other 3 have to be heads. So these 2 are going to end up being the same. And we know that the formula for it is going to be this. In our next example, we say, how many ways are there to form a committee of 3 people out of 5 total? Now, there are multiple ways of solving that problem, but the way that I want you guys to think about it so you can link it to these other ideas is think of your 5 people individually, and then I'm going to put blanks here, and every blank spot should be filled in with a yes or a no. So let's just abbreviate that Y or N, right? And if they get a yes, that means they're in the committee, and if they get a no, that means they're not in the committee. So I need 3 Y's and 2 N's. So I could have it so that it's these 3 are in, these 2 are out, right? Or I could have it where these 2 are in, this guy's out, this guy's in, that guy's out. And it doesn't take too long before you realize that this problem is the same as this problem, which is the same as the other ones. So this, again, there are going to be 5 choose 3 ways. This is where I think the choose 3 makes the most sense. I got 5 people, I need to choose 3 of them. So 5 choose 3 sounds right. And it's the same thing as saying, I've got 5 people, I'm going to choose 2 to kick out. Right? That's really no different from saying I've got 5 people, I'd like to choose 3 to stick around. So these 2 things end up being the same, and we know the formula for it is this. Okay, the one that I think is the weirdest for people is the binomial theorem. So that's when you've got a binomial term and you're raising it to some power and you have to expand it and figuring out what the coefficients are. So in this one, x plus y to the 5th, I want the coefficient of x cubed y squared. And the ways we can figure that out, now you could sit there multiplying and multiplying and multiplying a ton. But the shortcut for it is to actually think of it like this, and then to say to yourself, well, how do I get 3x's and 2y terms? Right? So I need an x, y, y. So the x cubed y squared. One of the ways that you can get it is when you multiply this out, you're going to take every single combination you can of x's with y's here. You're going to pick an x and a y from here and multiply it with an x and a y from here and multiply it with 1 from here and multiply it with 1 from here and multiply it with 1 from there. And if you did that with every possible way of doing it, you'll get the full polynomial. So what I want to do is this. Let me put that back. I'm going to pick this x, this x, this x, that y, and that y to multiply together first. That'll give me an x cubed y squared term. So it's this one, right? But I didn't have to pick the first 3 x's. Maybe instead, whoops, I'm going to pick the first 2 x's, then a y, then the x, then the last y. So in that case, I would end up with x, x, y, x, y, which is also an x cubed y squared term. Well, maybe I want to pick this x, whoops, this x, this x, this y, and this x. Oops, keep doing that. So if I do that, now I've got x, x, y, y, x, which is another x cubed y squared term. If I keep doing this, you can start to see that I'm really just coming up with as many words as I can that have 3 x's and 2 y's. So if I keep writing this out, I'm really not doing anything different from this problem or the one before that or the one before that or the one way up here where I'm listing off all the words that have 3 A's and 2 B's. Instead, I've got 3 x's and 2 y's. So the coefficient down here is going to be 5. I've got 5 letters, and I'm choosing 3 of them to be x's every time. And that's really no different from me saying, okay, I'm going to raise it to the 5th. I'm going to raise it to the 5th, and I want to pick the y squared terms. Right? The other 3 have to be x's. So this again, 5 factorial over 3 factorial, 2 factorial equals 10. Okay. So over here, I've already made the full Pascal's triangle with, whoa, oh, great, stuff shifted over. Let's see if I can fix this. Oh well. I don't know what happened to everything. I lost some stuff. Like 4 choose 3 for some reason is gone. And 3 choose 3. I don't know what happened there. But anyway, this is generally the triangle. One of the nice things is that if you have to expand an entire polynomial like x plus y to the 5th, let's say, well, you're going to get an x to the 5th term, an x to the 4th y term, an x cubed y squared term, an x squared y cubed term, an x y to the 4th term, and then a y to the 5th term with x to the 0. And the coefficients all come out of here. This is really y to the 0. Well, we just figured out that if it's x cubed y squared, it's the same thing as 5 choose 3 for the coefficient, right? Because I've got 5 letters, and I need 3 of them to be x's, which force the other 2 to be y's. Well, this one is going to be, I've got 5 letters, and I want to choose 4 of them to be x's and the other one to be y. And this one, 5 choose 0, and 5 choose 4, and 5 choose 5. Wait, did I mess up? Oh, I'm sorry. I did. This one would... shoot. I went all the way through this video. Let me start over. Let me get rid of these guys. Okay, this one is to the 5th and 0 there. Okay, so this one right here, I've got 5, and I'm going to choose, I've got 5 letters here, 5 x's and 0 y's. So I want to pick all of them to be x's. This one, I've got 4 x's, which forces the other one to be a y. This one, I got 5 letters, I want 3 of them to be x's. This one, I got 5 letters, I want 2 of them to be x's. And this one, 5, 1 of them to be x's. And then 5 with no x's. Okay, now that's really no different from me saying I've got 5 letters and I want none of them to be y's. And I've got 5 letters and I want 1 of them to be y. And you can work your way down and you end up with 5 choose 5, y to the 5th right here because I chose all of them to be y's. So it doesn't matter if you think in terms of the x's or the y's. In fact, if you just wanted to switch these two randomly for some reason, you could and it wouldn't change anything. And then what most textbooks do is they start with the 0 one and then they work their way up to the big one, because in Pascal's triangle, all those coefficients are just staring right at you here. For some reason, this one disappeared. This one is a, what is that? 4, 6. This one should be 10. Yeah, I don't know what happened with all the numbers there, but oh, these all got shifted. This one's a 6, that one's a 4. Sorry about that. This is 3, that's 1. That's 1. Okay. So hopefully that helps a little bit. I think it does take time to sink in and really sort of sit in your brain properly. So give it some time if it hasn't. Watch the videos a couple more times if you need to. And definitely come find me if you have any questions.